Good afternoon, everyone, and welcome to the Communication and Signal Processing Seminar. Let me start by first thanking the research areas for sponsoring this. This is NCIS, and which is Network Communications and Information Systems, and SP, Signal Processing, Machine Learning, and Image Processing. So I'm delighted to introduce Sujay Sanghavi, who's our speaker today. So Sujay is currently an associate professor and the Fluor Centennial Teaching Fellow at the University of Texas, Austin. He received his PhD in ECE and MS in math and ECE from the University of Illinois. This was many years ago now. And he was a postdoc at LIDS at MIT soon after his PhD. So Sujay's research focuses on rigorous methodological innovations in machine learning using ideas from optimization, statistics, and graph theory. He has received his early career award from NSF and DoD, and currently leads the NSF Tripods Institute and Foundation for Data Science at UT. He's also been interested in learning from and applying his ideas in industry. In fact, he spent quite a few stints at industries. He's been a visiting scientist at Google Research, trying and failing to match them or beat them, I don't know. A senior quant at Engineers Gate, and is currently a principal research scientist and Amazon scholar at Amazon. I should add that I know Sujay very well for a long time. We are actually academic brethren, sharing the same PhD advisor. Of course, he's gone on to do a lot more interesting things in machine learning, and I'm still pottering away on the usual stuff. And so with that, I'll let Sujay take the stage. I will give more stories if you want, but I don't want to embarrass him too much.
Yeah, I mean, I was going to say that there's plenty introduction. Thank you, Vijay. Yeah. Okay. Yeah. So I'll be talking about kind of a collation of work I've been doing for in the last couple of years or so. Feel free to stop me at any point if you have any questions. The easiest way, I'm not going to read the chat or anything, just unmute yourself and ask a question, right?
Yeah, that's usually how we handle it. I sometimes monitor chat, so I can always stop and interrupt you as well. So.
Okay, right, yeah. All right, yeah. So I'll be talking about model agnostic robustness. So let's just get into what that is and what I mean. Okay, right. So let's take a brief background or motivation for where we are right now, right? So most large ML models right now, most modern ML models are kind of large and unwieldy, right? In the sense, and by unwieldy, I mean two different things. One is just operationally, right? They are kind of complex to train, and I mean, as compared to more simple models of before, like an SVM or a decision tree. Right, these are much more logistically complex to train because the data is large, the model is large, and so on. And then, from the kind of analysis or understanding side, it's hard to get a principal understanding of why they work, right? So with this background, the context of this work is how do you get robustness in the face of these issues, right? And so we'll focus on three cases. Or three specific instantiations of this of the robustness issue. So one is where just imagine we have a labeling problem, which is basically a classification problem, and we have, but our training data has errors in the labels. Okay. The second case is where we have there are so in case one there are errors in the labels but not errors in the features. In case two, it's similar, except in the sense that there is no errors in the features, but the data is just spurious, right? And this is in the context of generative models. I'll define all these things, right? And the third case, which we'll get to only if we have time, is if we actually have errors in the features themselves.
So Sujay, there's a question: what is SGD?
SGD is stochastic gradient descent. I'll define it in a couple slides. But it's the most / the only way to train modern machine learning models. Okay, so let's take a specific example, right? So let's take a pretty popular data set, CFAR 10. So what this contains is, about 60,000 images organized into 10 classes. And these are the labels for that. And the classification problem is, given a new image, label it with one of these labels. So it's kind of like a baby image labeling problem. So this is an off-the-shelf data set. Let's pair it with an off-the-shelf neural network. Let's say wide resonator 16. This is a pretty popular architecture. And this is like a moderate size neural net. And so, if we just train it from scratch, this is like a homework problem in a neural networks class. We get 92% accuracy, right? The state of the art with this architecture is a little bit better, but it doesn't really matter for us. So we get pretty high accuracy when we train on the clean data set, okay? Now, suppose we change the problem up a little bit, right? And we say that some of the labels are in error, right? And so specifically, I'm concerned with what I call systematic label noise. So in systematic label noise, 25, let's pick some number, let's say 25%, right? So 25% of all images that are labeled cars are instead have their labels changed to horses, right? And things that are labeled birds are changed to truck, and so on, right? So it's systematic, right? Like all the 25% of the horses that are in error are labeled truck, right? As opposed to random errors. Okay, so if we have systematic label errors, and we just and we have this as a data set, so obviously we don't know which images are in error, but we do know that 25% of them are in error. Okay, right? Then the question is, what should you do, right? So the first answer is, let's ignore the fact that they're in error, and let's just train the model anyway, right? So let's follow the previous workflow that we had before, right? Assume the data set is clean, even though it's not, and let's just train the model and see what happens, right? And so that's what we see on the right-hand side, right? Which is, the y-axis is test accuracy, and the x-axis is the size of the training data set, okay? And, accuracy improves as the size of the training data set improves, right? But we see a big drop between what I call the oracle and what I call the baseline, right? So the baseline is taking a bad data set, ignoring that it's bad, and just training it, right? The oracle is, if you knew, so there's a strong oracle and a weak oracle. The strong oracle knows precisely which are bad and makes them good, right? So it uses 100% of the data. The weak oracle knows which are bad and ignores them, right? So it uses only 75% of the data. Okay. Both the oracles are unrealistic, and they are pretty accurate, right? But ignoring the fact that your data set has errors results in a huge drop in accuracy, which is not, which you cannot make up for by just having more data. Okay? So, so this is kind of like my motivation slide, right? Which is, if we knew that there are 25% in error, what is it that we can do?
I have a question here.
Yeah.
So this 25%, it remained constant as you increase the size of the data set?
Yes.
Right.
Yeah. Yeah. So there is an overall number of 50,000, right? And I just randomly subsampled the training data to get different points on this x-axis. Right?
Yeah.
So on average, every subsample has 25%.
Right.
Okay. Right. So this is the setting we are in, right? We know the data is bad. What can we do? So that was case one. Now let's look at case two and generative models, right? So what a generative model is a little bit different from classification, right? So the generative model task is the following. We have a bunch of training data. Let's say in this case, it's the simple MNIST, which is another popular data set. And what MNIST is a set of handwritten digits, right? So, these are handwritten digits. And what we're interested in is the generative problem, which means that we want to make fictitious digits, right? So we want to be able to generate, images, I guess, pixels that look like digits, but are actually not written by any human. They are written, they are generated by a computer, right? So the way you do that, one way you can do that is by GAN, like which is a kind of generative model, right? For our purposes, it's a feed-forward neural net, again of moderate size. And so, we're following the same theme as before, right? This is an off-the-shelf data set. This is an off-the-shelf neural network of moderate size, right? And the way this thing works is once it's trained, you give it a random vector of length 100, like a random Gaussian vector, right? And you pass it through this thing, and it will generate an image. And that image will look like an handwritten digit, right? So, for example, what I've shown here is a bunch of handwritten digits, actually, a bunch of digits that are the output of this neural network. They look like they're handwritten, but they're not really, right? They are generated by this neural network. So this is a baby generative model, right? And as of now, this entire slide is on clean data. So which means that all my training samples are actually handwritten digits. And then I run it through this neural net, and I get some pretty good looking output, right? Which is handwritten digits, or things that look like handwritten digits. Okay, right? So the bad data case here is, suppose 80% of my data, right, is from the distribution I want to model. In this case, the distribution I want to model is a distribution of handwritten digits. Let's think of it as some abstract distribution, right? So 80% of my samples are from the actual distribution I want to model. 20% are from a completely different distribution, right? In this case, we chose fashion MNIST, which is a different data set designed to be a drop-in replacement for MNIST, right? So what a fashion MNIST is little pixelated images of fashion accessories, like handbags or T-shirts and so on, right? And so if I have a data set which is 20% fashion MNIST and 80% handwritten digits, but obviously for any given, like for sample number 103, I don't know which of these two it is, right? If I just follow the standard training process as I showed before, right, then I get very low quality output, right? So first of all, I neither get handwritten digits nor do I get fashion MNIST. Was there a question? Yeah.
No,
so,
go ahead. Yeah.
Sorry. Yeah. Okay. Yeah. So, and again, we have the same question here, right? Like our motivation is, if I knew that 20% of my data is bad in this generative model setting, what can I do differently? So that's the question. So note in both these questions, I have told you minimal things about the actual model. What is wide ResNet 16? What is DC GAN? I haven't told you, right? In some sense, we're trying to find answers for which that doesn't matter. Okay, so why do we want that, right? So the principled approach to doing robustness is to actually understand what is the model, right? Like, are we doing PCA? Are we doing regression? Are we doing clustering? If it's an unsupervised problem, what is it that we are doing? Let's understand it and let's make it robust, right? That's the principled approach. Unfortunately, that principled approach is not often tenable, right? Because of the two issues with modern machine learning models. First of all, they're very big, right? And so there is really only one way to train them, right? There are many ways to do PCA, but there is only one way to really train a large neural network model, right? So that's one. And the other thing is that, to design a robust variant of a model, we need to understand how and why the model works. And we don't really have that for deep neural nets. So those are the two issues why we take the approach we take, which is model agnostic, right? In some sense, what the model is doesn't really matter.
So Sujay, actually had a big question before you.
Yeah.
In there, I mean, your generative model thing, you said it was like polluted data.
Mm-hmm.
But why should I not think of it as basically a mixture of two things, and I want to learn the mixture and output the mixture? I mean, why is that not a good perspective for that problem?
Yeah, so that is a good perspective for that problem, right? So for example, if you took a bigger network which could overfit better, you may be able to get a mixture model of the two, right? But say your goal is not that, right? Like your goal is that there is an inlier distribution and an outlier distribution, right? You don't know what either distribution is a priori, but you know that 20% of your data is outliers, and so it's a question of what the task is, right? Like one task is, hey, can you make a generative model for the mixture, right? That's not my task, right? My task is to make a generative model for the 80% of the data that's good.
Okay.
Yeah. Yeah. So yeah.
Another question, Sujay. This is Clay Scott.
Mm-hmm.
You can modify the loss function. So like with label noise, you can use what so-called corrected loss. So I don't know about GANs, but can you comment on whether at some point in the talk, can you comment on how what you're proposing might compare to that type of approach?
Yeah. So I think that's best stated in the classification setting.
Yeah.
So if you don't mind, let me come back to that after.
Yeah. Okay.
Yeah. But that's a good. This is not the only way to deal with labeling. Okay. Any other questions? Okay, so before we get into our solution, let's take a step back and see how the typical training workflow for an ML model, right? So the first step is you have an ML model with some parameters theta. These are like the weights of your neural net, and then for every sample you have a loss function which relates the parameters to the sample, right? And then your overall training objective is just like an ERM objective of like minimizing the sum of losses. Right. So for example, if this was linear regression, then the loss would just, theta is just your like regression vector, and then yi is just, your samples are xi, yi, right? Where x is the feature, xi is the feature vector, yi is the response. If you have a feed-forward classifier, then your si is the label, the label and the image, and your theta is the parameters of this model, and the loss is maybe like a multi-label cross entropy loss. If you have a GAN, then the way GANs are trained is that you finally need a generator network which takes in a random vector and outputs something that looks real. But the way you train it is you train it jointly with something else called a discriminator, which you're going to throw away later, right? And so you train both of them together in a kind of game theoretic fashion. So the generator, generates a candidate sample, which initially will be garbage, but hopefully will become better soon, right? And then so you take that and you take a sample of the real data, right? And then you pass both to this. There are many ways to do this, but one way is like, you pass one of them to the discriminator, which is a binary classifier, which says, and the job of the discriminator is to figure out whether the sample given to it was fake, which means it came from the generator, or whether it was real, and since it came from the data, right? And so if you train both of these jointly, they both become better and better, right? And finally, at the end, you have a really good generator and you have a pretty good discriminator, and you throw away the discriminator and you output the generator as your neural network for generating new handwritten things that look like handwritten digits. So in this case, the per sample loss is the output of the discriminator, which is a binary classification loss. Okay. Right. So with this setup, right, we want to minimize this kind of loss function, which is the minimum of a sum of individuals per sample losses, right? And the way we do that is we break up training into epochs, right? So an epoch is just a length of time which contains several updates to theta. So we start from some theta, right? Some guess, let's say random, right? And then we take a batch of samples. We evaluate the gradient of the loss on each of the batches, and we average it out, right? So this is stochastic gradient descent, and then we update theta. right? So if our data set size was not too big, then B would be every single sample, and this would become gradient descent, right? But because our batch size, because our data set is very big, we randomly sample B data points and have this like random gradient, which is called stochastic gradient. So that is stochastic. So this is stochastic gradient descent, right? And after each epoch, we change some, like we change the step size eta, and we can change other hyperparameters as well, right? But typically, the step size is the parameter that's changed between epochs. Okay, so this is the default kind of baseline way to train a neural net. So what we want to do is we want to change up this approach, right? We want to modify this approach to make it robust. So our approach, is pretty general. I'll tell you what approach is, but it's pretty general in the sense that all it really needs is that your estimation is done by a sum of losses, and conversely, for any given theta, you can assign a per sample loss. So you just need a per sample loss, and you need estimation by minimizing a sum of losses. As long as these two things are true, you can just apply our method out of the box. Okay, so what is our method, right? So the motivation for our method, although this was a post facto motivation in the sense that we found this quote after we wrote the paper, right? But there's a quote from Regression, and it says that he wrote it in the context of linear regression, but it's applicable more generally. So it says that if there are some errors that appear too large to be admissible, then those equations which produce those errors should be rejected because they probably come from faulty experiments. Right? So he was talking in the setting of solving a bunch of equations when some of them may be faulty. All right. More specifically, our direct motivation comes from an idea in statistics called trim loss, right? The standard way to train a neural to train a model is to just minimize all the losses over all the samples, right? But if I knew that only a fraction tau of my samples were legit and the others were not legit, then I should ignore them, right? And so I can define a different loss function, which does a joint minimization over the set of samples that I think is legit and the theta that fits those samples, right? So this previous summation was a summation over all samples. This new summation is a summation only over my chosen set, right? And now I am jointly minimizing both the chosen set and the theta which fits that chosen set. Any questions about what trim loss is? Okay, right. So, trim loss has been an estimator, that's been proposed for at least 30 years, and it has good, it has pretty strong robustness properties, right? The issue with it is computational, right? There is this joint minimization between theta and S is a, naively is a search over subsets of this of the entire sample set. So this is infeasible. Like even for linear regression, in the worst case, you can't, it's NP hard to solve trim loss. So looking at linear regression a little bit more closely, all right? So the standard training is just, to minimize the squared loss, and the trim loss is this, right? And it's NP hard. All right. So how do we get around it? Right. So the way to get around it is to make it more computationally efficient by doing an approximation of this joint minimization. And the approximation is by a simple idea, right? Which is that if we knew what the good samples were, we could get a new model. We could get a good model pretty easily, right? So which means if I knew the S, then I could find a theta. And if I knew a theta, I could find an S. right? So each sub-step of this overall procedure is very easy to do, it's trivial, right? It's just that when you try to do them jointly, it becomes NP-hard. Okay, so that's the basic approach, right? The iteratively alternate between selecting a good set of samples and training a model on this good set. So to select a good set of samples, what do you need to do, right? You take, like, I'll take my current parameter, I'll take my current model, I'll evaluate the loss on every single sample, and I'll pick the samples with the lowest loss. Right? So I'll pick the, I have some budget. Let's say, I know that 25% of my samples are in error. So my tau is 0.75, right? And so I'll pick the 75% of samples that, I think are legit as given by the current model. I'll call that my good set. And then I will update my theta by just minimizing the losses on what I think is the good set. And I keep alternating between them. So one is trivial sorting. The other one is standard model fitting, right? But on a subset of the data. Any questions about the approach?
Hi, this is Sudeep here, Sujay. So this seems awfully similar to coordinate descent. Is that like a good way to think about this?
This is not coordinate descent, right? So what coordinate descent would do is, like imagine theta is a d-dimensional vector, then it will minimize individual coordinates of theta one at a time.
No, I meant between S and theta. So you're first optimizing for S and then optimizing for theta, keeping the other fixed.
Right. Yeah. So in some abstract space, if you think of like a 2-coordinate space where one of the coordinates is the entire parameter vector and the other coordinate is the sets, then yes. Yeah. But that's just a 2-coordinate space. So, it's closer to EM. This is actually like hard EM.
Gotcha. Thank you.
EM is expectation maximization.
Hey, Sujay.
Yeah.
This Lei here.
Yeah, hi.
Hey, yeah, so I don't know whether you're going to talk about it or not, so just want to ask that. So if we look at like not intentionally inject noise, just the random noise, right? Does your approach provide any benefit? I'm thinking like even doing that will give us some benefit, right?
Yes and no, right? So that's a good question. Okay, let me take a quick detour to answer Lei's question. So, okay, here, if you remember this plot, right? This was training data set size and test accuracy. And if you see training data set size, remains below the kind of outer bound of what we could do if we had an oracle, right? So this is what happens with systematic noise. Now imagine you had random noise, right? Where 25% is still in error, but the errors are just sprayed all over the place, right? So that the horse images that don't have the correct label horse, they have like equally likely every other label. If you have that, then, and if you put that plot here, I haven't put it, but we have it in the paper. If you put that, it kind of goes up, right? Like as you have more and more training data, you do recover some of the accuracy, right? So if you have random noise, it still helps to do, what I'm suggesting, right? But if you had a tremendous amount of data, so for example, the MNIST data set, right, has an enormous amount of data for the machine learning problem it's trying to solve, right? So if you had this kind of thing for MNIST, right, it would not be a problem, right? Like your 25% of random errors would be fine. Just run it on the entire data set and you would still be fine. Right? I mean, you'd be a little bit better with this more sophisticated approach, but you don't really need it.
How about the like impact of the error distribution? For example, if the heavy tailed error will have more benefit of doing this? Because you have more like outliers, right?
Yeah. So you mean heavy tail in the label errors. So there are some labels which are much more likely to be in error, and there are some labels which are much more likely to be the wrong labels, right? So if you have something like that, then that is closer to being systematic noise. And so there you'll have like, I mean, I would guess that you'll have more of an effect. Like your data set size won't just help you.
Great, thanks.
Okay, right. So just to recap, like, so our a basic approach, just works for like anytime you have a per sample loss function and way to estimate theta from a subset of the sample, right? And so we have two results, and two flavors of results, and I present both. So the first one is a theory result, which in which we kind of fully analyze this approach for a simple error model, which is mixed linear regression, and I'll tell you what that is. And then I'll show some experimental results for image classification and generative models. Okay, so let's look at the theory results for a little bit. So we are in the setting of mixed linear regression. So what is this setting, right? So standard linear regression is for each sample, there is an underlying theta star, which is the ground truth, and yi is generated as xi transpose theta star plus n, right? And all the samples come from theta star, and given yi xi, you want to find theta. You want to find the theta star, right? That's linear regression. Mixed linear regression is that every sample, let's say a mixed linear regression with two possible theta stars. So there is a theta star 1 and a theta star 2. And every sample, has a yi that's generated either as x transpose theta star 1 plus noise, or x transpose theta star 2 plus noise. One of these two. You don't know which one, right? Maybe half and half, or maybe 40-60 or whatever, right? So there is, and so finally what you get in the samples is a mixture of some samples that came from theta 1 star and some samples that came from theta 2 star, but you don't know which is which. And so the mixed linear regression problem is, given these samples, find the underlying theta stars that generated them. And so, like if you want to think of it as a picture, think of the blue dots. Okay, so like the x-axis is x and the y-axis is y, right? And think of the blue dots as coming from theta star 1, and think of the red dots as coming from theta star 2, right? And now the mixed linear regression problem is, if I just give you all these points without telling you their colors, can you find out theta 1 star and theta 2 star? That's the mixed linear regression problem. It's a pretty standard mixture model style problem. So what we're going to do is we're going to analyze we're going to apply our algorithm to this problem and analyze it. Okay, where does something like this come up? So this actually comes up in, say for example, you're doing a recommendation system using matrix factorization, right? So here's an example of a recommendation system many of us see almost every day, right? When you log into Netflix now, you get this kind of first page, right, which is who is watching, right? And so this is me and my family, right? So who's watching, right? And why does Netflix want this? Netflix wants this because it's trying to recommend to you based on your history, but it doesn't know who you are, because it could be you, it could be your wife, it could be your kids, right? And you have very different tastes, right? And so they want to disentangle it, right? So if recommendations were based on matrix completion, then it would exactly become a mixed linear regression problem. This is a side tidbit. Okay, so back to mixed linear regression, right? So we want to find these different thetas given xi and y. So how do we apply our approach? So our approach is that to apply our approach to this problem, we'll take the tag that we actually want to find only one of the theta, like only one of the theta stars, right? We don't want to find all, we just want to find one. Let's see if we can find even one of them, right? So for example, if you just did least squares on the entire data, you would find none of them, even with infinite samples, right? But so you have to do something else, right? So let us just try to find one of them. Okay. So what is the process? Fix a tau, right? Like, so fix some fraction of the data that you think is represented by your sample, right? And then take an initial guess for your theta, fix a tau, and then do our method. Right? So do least squares on these samples. Right. So specifically, you first start with a theta that is an overall least squares on the entire data set. And that will give you some theta, kind of theta hat, which is the first estimate. And then you keep iteratively improving that estimate by picking a subset of the samples that have the lowest loss for that estimate, and then improving that estimate and doing this iteratively. Okay. So let me show you what happened, like what that process is in pictures, right? So let's say this blue and red was our mixture data set, right? And we don't know the colors. So we just do least square minimization. If we do least square minimization, we get some theta, that maybe looks like this, right? It's neither red nor blue. It's kind of like a mix between the two. So after we get that, which is this center bold line, then we take a range around it, right? So we keep expanding a band around this center until we capture, let's say, 60% of the points, right? So we have to pick some threshold. Let's say we pick 60%. So we keep expanding this band till we pick 60, till we reach 60%. So basically what this means is that these are the 60% of the samples with the lowest loss. Okay? Now what I'll do is I'll ignore everything that's outside this band. And I'll run a linear regression only on stuff that's inside the band. Okay. Some of them are red and some of them are blue, but they only matter to me for the next step if they are inside the band, right? And if they are outside, I ignore them. So if I do that, then at least pictorially here you can see that there is more red and blue, right? Like a lot of the blues that are far away are canceled out, right? And so we have these blues that's kind of bunched up together. The reds are still up this way, right? So the next step will improve it a little bit better in the sense of bringing it a little closer to the right. Right? And now I solve my least squares again, and I get a new line. And then I repeat the process. I thicken this line to a band such that I pick up 60% of the sample. And now for the next step, I'll ignore everything outside and I'll only fit on stuff that's inside. And I keep doing that. And as you keep doing it, you get closer and closer to, I mean, like at least in this picture, you can kind of get an idea that, if you start closer to one of them, you will get closer to that one, provided you're 60, provided certain things are true, and I'll tell you what they are, right? But this is the basic idea or intuition behind the thing. Okay, so here's the informal theorem. I guess, so let's start from a given theta, right? Given this, we'll have linear convergence to the closest underlying true parameter. So remember, with mixed linear regression, we had two ground truths, right? We had a theta 1 star for the blue, and we had a theta 2 star for the red, right? And so, and we started from some theta, right? Let's suppose that theta was closest to it will be closest to one of them in terms of angle, right? So let's say it is closest to the red one, right? Then, so we need that as one condition. And the second condition is that it's going to, that our algorithm retains a fraction of the data. The fraction of the data it retains should be, which is tau, should be less than the true fraction accounted for by this closest ground truth, right? So if red has only 50% of the points, but I am retaining 60% of the points in every iteration, then I'm not going to converge to red. On the other hand, if I am retaining only 30% of the points and 30 is less than 50, then I will converge to the red. And so that's what the theorem is saying. So we get linear convergence to the closest thing, provided our threshold is decent.
This is convergence as the sample size grows. Is that the kind of convergence you mean? Like a consistency result?
Right. No. So this is convergence in terms of the number of steps we take in my algorithm.
With noisy data, you're not. So that theta star is not the true latent parameter. It's an estimate of it, I guess, then.
Yeah. Right. Yeah. So.
Okay.
that's a good point. Let's split it into two. So first of all, if there is no noise, right? This is still not.
Okay.
Yeah. So we have a noisy result as well. But let's first understand the noiseless result. So the noiseless result is, which means if there's no noise, right?
Yeah. Okay.
There are basically two sets of equations, and then you will get, you will exponentially converge to the closest one.
Okay.
And you will reach it exactly, right? Now, if you do have noise, you will reach to a ball within that, right? So
Okay.
you'll have linear convergence. So it's like, the typical linear convergence is like the error at theta t plus 1 is less than some constant times the error at theta t, right? But now you have a plus, you have an additive term. And so basically that means that after some time, the additive term is what dominates.
Got it. Thank you.
Okay.
Yeah, so there must be some performance trade-off in terms of this tau, right? Intuitively, if like tau is really small, then we will lose something. Can you comment on that?
Yeah, I will, right? So let me skip to the formal theorem, and that will exactly quantify what you're saying.
Yeah, sure, thanks.
Yeah. So, in our paper, we have deterministic conditions for when, which means the xi's come from fixed design matrix, or we have simplified conditions when the xi's are IID Gaussian. So let's just go for the simplified conditions, right? So, okay, what this says is, and this is in the, this is in the noisy case, right? So my current estimate is theta hat. The closest thing is theta 1 star, right? So among the different components, I end up being closest to theta 1 star, right? And let's say that the fraction of data whose ground truth is theta 1 star is bigger than the fraction that I'm retaining in every step, right? So which means I was lucky and I guessed tau correctly, it was small enough. Then the next iterate, right, will satisfy, its distance from the ground truth will be less than some constant, which is less than 1 of theta hat minus of my current error plus the noise. So this answers the previous question also, right? So, once this becomes too small, you are kind of, bouncing around in a noise ball, right? Yeah. So, but to answer Lay's question, right? The number of samples I need in every iteration is inversely proportional to tau raised to 4, right? So I need my fraction to be smaller than tau 1 star, but I do pay a penalty for making it too small, right? So I cannot just pick 3 samples and refit my theta. That's going to be pretty bad. Does this answer your question, Blake?
Yes, thanks.
Yeah. So this is the theorem more formally for the sim, and like this looks this clean because everything is Gaussian. Right? Okay. So this gets us to one component. What do you do if you have, but what if you do if you want to actually solve the mixed linear regression problem, the original problem, which has multiple components, right? So then what you can do is you can just peel and repeat, right? So you start from a theta, you get to the closest theta star, then peel means that once your algorithm, like once my process has converged, I am going to look at the tau fraction of samples that are closest to it, and I'm going to remove them from the data set, right? And then I'm going to do the same thing that I did before again. Right? And then I'll get another component, and then I'll remove that, and I'll peel and repeat. So this gives a state-of-the-art performance, but it's a little bit, state-of-the-art is a little bit of cheating in the sense that we assume that we have knowledge of the underlying tau stars, which means the fraction of the data that comes from each component. We don't know what fraction, like we don't know which samples, obviously, and we don't know what the theta stars are, but we do know the tau stars. Yeah, so it's state of the art with an asterisk for mixed linear regression. Okay, so as with any talk in machine learning, right, the natural question is, but what about deep learning, right? Like like this, like so far, I mean, I guess, the method was motivated by applications in deep learning, but all results I've told you about are theory results for linear regression, right? So what about deep learning? Specifically, it doesn't exactly carry over right away, right? In the sense that, and the reason is that neural networks are a very powerful function approximators, right? So if you train a neural network to convergence, right, they are heavily over-parameterized. And so what will happen is that the training loss for all samples will go to zero, right? So just remember what we are doing, right? Like we are training a model on some samples, and then we are evaluating a loss on the same samples, right? So we are evaluating training loss. And now it's been observed, and it's pretty easy, it's pretty well known that if you train a neural network, then the training loss will become zero, right? Because so how can you apply this method if all losses are zero, right? Because I'm going to pick my good set to be the set with the lowest losses, right? But if every loss is zero, then it doesn't really work. So the answer to that is don't train the neural network to convert, right? Just train it for one epoch or a few epochs. So specifically here, we have, what this is showing for different setups. Let's look at B, which is systematic error in labels, right? So on the y-axis is accuracy on the training set of the model, right? And on the x-axis is the number of epochs that we trained the model for, right? So as you train a model on a mixture of good and bad samples, right? It's a mixture of good and bad samples. Then for initial epochs, clean sample, it has a much higher accuracy on the clean sample, and it has a lower accuracy on the bad sample. The reason being that there are more clean samples in the data than there are bad samples. Right? As you train it more and more, these accuracies start to converge because the model, is overfitting, right? Sorry, not overfitting. It's taking the bad data more into account. Right? So what you want to do, and you want this gap in accuracy, because this gap in accuracy means that if you filter down the samples to a good set, using the accuracy of the model on which it's trained, then you will be more likely to keep a clean sample than you are to keep a bad sample. And that's what you want, right? Like you start with 60% clean samples, and finally in your filtered set, you want like 70% clean samples. And then and then the next time you want like 75% or 80%, right? So you want that kind of boosting of the data set. And what this shows is that kind of boosting empirically does occur if the model isn't trained all the way to converge. Okay. Right? So yeah, I'm just repeating what I'm saying. Like there's a difference in training loss in the initial epoch, right? So what that means is that instead of that, previously we had a picture where we just had epochs one after the other. Now instead you train a model for an epoch, then you do sample selection, and then you train a model for an epoch again, and then you do sample selection, right? And if you keep alternating it in this way, right, then that will give you a pretty good adaptation of our method to deep network. Because at the end of one epoch, so think of one epoch as like one pass of the data, right? The model is nowhere near convergent.
Hi, Sujay. This is Qing. I have a question.
Yeah.
So why not do you evaluate your model on validation set to determine how good a model trained instead of focus only on training set?
Okay, right. So suppose I have a clean validation set, right?
Yeah.
That clean validation set will show me that I have a big error after epoch one, because epoch one has bad data in it, right?
I see.
Right. So the point is not to evaluate the model after epoch one. The model after epoch one is already bad. I can already tell you that, right? the point of sample selection is to, the point of evaluating a model on the training data is to subsample the training data itself.
Mhm.
Does that answer your question?
Yeah, thanks.
Hey, Vijay. So
Yeah.
I guess it's clear, like for epoch 1, like you get a better performance on the valid data than the systematic data, error data. But how does that like propagate over epoch 2 and 3? Can we always guarantee the performance better on the real data?
Well, I mean, it depends what you mean by guarantee. Like there is no theoretical guarantee. This is not a theoretical plot, right?
Right.
But
Can we guarantee whether there's always positive feedback, not like negative?
Yeah. So we have observed that the number of good samples that are retained by the sample selector does increase.
Okay.
Right. Like that's what you're asking, right?
Right.
Yeah. So they do, right? For the simple moderate size networks that we train.
Thanks. Yeah.
Hi, Sujay.
Yeah.
This is Yutong. I have a quick question. So I was wondering, when you have a mini batch, do you assume, say, the mini batch has 75% clean data and 25% dirty data, or do you not assume that?
So I don't change what happens in a mini batch, right? So each of these little things is your mini batch, right? It is like there are several of them within an epoch, right? So within the mini batch, I don't do anything.
Okay.
I leave it as it, right? Yeah.
So in a mini batch, like you could have more than 25% dirty data, from the
just by randomness.
So I was wondering if, like, hypothetically, if all the mini batches we could make it so that each mini batch has 75% clean data, would it be possible for us to not do early stopping? Because let's say you get to a good model and all the mini batches have 75% clean data, and somehow you figure that out, then by taking the top 50%, you will never touch the dirty data. And
so
yeah.
Are you doing selection within the mini batch?
Yeah.
Let's say you're, previously you took a mini batch of size 100 and used all 100 samples, average them and, use that as your SGD update. But instead of that, now you'll say, oh, I'm not going to use all 100. I'm going to just use 75.
Yeah.
Right. Yeah. So you could do that, if you pick the 75 that have the lowest loss within each mini batch, right? That's what you're saying.
Yeah.
Yeah. So that does work, right? It is more computationally. So we have analyzed that as well. That's, I gave a bunch of papers to Vijay, and that was one of them. It's in AI Stats 2020. Yeah, that does work as well. Again, for mixed linear regression, theoretically. Practically speaking, it's kind of heavyweight, right? Like,
I see.
Because each mini batch now becomes slower because you have to run an evaluation. Like it's at least 2x the work and maybe more. Right? Yeah, I mean, the way neural networks are, like, because of backprop, the computational effort in evaluating a gradient is similar to the computational effort of actually evaluating the loss, right? So you are doing kind of 2x the work of within each epoch, right? While here, that's not the case.
Right.
Yeah, but that being said, it's a good idea and it does work.
Okay, cool. Thank you.
Okay. Right. So, okay, we went over what the algorithm already is. So here are the results, right? So ITLM is iterative trim loss minimization, right? That's our algorithm, right? And so in this table, we have 3 different data sets of 3 different complexities. MNIST is the simplest, C400 is the most complex. And we take different levels of how many errors we have. So this is like 60% of the labels are good. This is like 90% of the labels are good. right? And the baseline, is hit pretty badly, right? When there's a lot of labels in error. The oracle is fine. This is the weak oracle, right? So it just knows which data is, what data is bad and ignores it. And ITLM, recovers a lot of the loss, or a lot of the hidden performance is rectified by ITLM. Right? And we see this across data sets and across levels of corruption. Okay, so I have 4 minutes. I'm wondering what I should say. Okay, let me quickly say how I would apply this to generative models. So as I mentioned, in a generative model, there are actually 2 models, right? And there's generative discriminator. And so we're going to, have theta be the weight of both the generator and the discriminator, right? So theta is what we actually want to learn, right? And as you will, recall, the way it's trained is you take a random vector and you make a sample. You take that and you take a something that actually came from the data set you want to model, right? So this is the generated image, this is the real image. And then you put both of them one after the other into the discriminator, which is asked for each of them to say whether it's real or generated. And then based on whether it makes an error or not, you update the parameters of the discriminator and the generator, right? So if it makes an error on the real, you update the parameters of the discriminator. If it makes a mistake on the generated, you make an update of both the discriminator and the generator. Right? And so both are learned together, both are randomly initialized, both are learned jointly, and they are trained to, and then finally the discriminator is thrown away and you use the generator. Right? So now the problem is we don't know which samples are spurious, right? Because in our data set, 80% of the samples look like this, which means they're nice, and 20% look like this, which means they're spurious, right? And so when you do this, we don't really know which training samples are spurious, right? And so that results in kind of a bad looking result. So how do we correct for it, right? So the first step is to just train with all samples, like do the baseline, right? Like just ignore the fact that 20% are bad, just train on all the samples. Then, go back and see what the model is. We have this discriminator. I mean, we also have the generator, but that's what we ultimately need. But the discriminator is what we are going to use to sub-select the training data. We take this discriminator, we run it on all the samples, right? We run it on all the training samples. Ideally, it should say real to every single one of them, right? But it will not. It will have some confidence, right? It will output a score between 0 and 1, right? And it will have some confidence of what, for each one of whether it thinks it's real or not, right? And then we take the 20% of the samples that the discriminator thinks are not real and throw it away. So we can do sample selection by the discriminator. So we run the discriminator only on every training sample, and you choose the fraction of the samples that look most real according to the current discriminator, right? And then you retrain the entire model, the discriminator and the generator from scratch on those parameters. Sorry, not from scratch, but for the next epoch, right? Only from those. So this is what it looks like pictorially. Like, this is iteration 0 is the baseline. And then this is the first iteration, second iteration, third and fifth, right? So by the 5th iteration of our algorithm, right, we are able to, look at an output that, pretty much looks like handwritten digits. It doesn't look as clean as if you had a clean data set, but it looks better than the baseline, just visually. And, you can also see you can also evaluate the output numerically, by looking at the discriminator and seeing which of the true ground truth samples did it think is bad, and which of the true ground truth samples did it think is good, right? So you can get quantitative results for GANs by looking at how good the discriminator was on the bad data set. And it's the same story as we saw in CFAR 100 and CFAR 10. Okay, here's a failure case, which is that this method doesn't always work. If the level of corruption is too high, then even if we know the corruption, we can't really correct for it, right? And this goes back to a question at the beginning of the talk, which is that you are given a mixture model. You want to pick one of the mixtures. But if it's like a balanced model where the data is almost equally likely to come from either one, then it's going to be very hard to correct for it. Okay, I think we are already over time, so I'll skip this errors and features thing. I'm happy to talk about it offline or in the meetings tomorrow, but there's no time for it today. Okay, so I'll finish up with an kind of interesting philosophical research question, I think, right? So this is what we did today. Iterative trimmed loss minimization for robustness, right? We alternated between estimating a model on weighted samples and then down weighting samples with the highest loss, right? And then kind of alternating again, right? So you have a model, you evaluate it on all the samples, you pick the ones with the lowest loss and you re-estimate based on those, right? Let's think of what is boosting, right? Boosting is the exact opposite. It's right. It's like you have a model, and now you evaluate the loss of the model on all the samples. You give more importance to the samples that were wrong, right? And you re-estimate the model for that. I mean, there are different settings. Boosting is used to learn a more powerful model, assuming there are no errors. And ITLM is assuming there are errors and doesn't really want to learn a more powerful model, right? But it's interesting that they are actually, they're similar looking algorithms that do the exact opposite thing, right? And so there's an interesting research question here of like, can we marry robustness and boosting, right? Like, can we have the best of both worlds of like having error in our data and stacking up weak models to make a powerful model? So I don't know the answer, but if anybody has thoughts, I'd be happy to discuss. Okay, I think that's it. I'll stop here since we're already over time.
Thanks, Sujay. So I was just going to add just a few remarks at the end. I was actually going to ask you about connections to boosting, but glad you mentioned it first. So this is mine is just minor stuff. So let me see if I can get onto that. Let me just share my screen. Okay. Oops. Yeah, I will. So I actually read through most of the papers that you sent me, and maybe I'll just the part where I was looking at, and again, this comes from my perspective, was more was looking at the stochastic gradient descent based risk minimization problem that you were mentioning. And there you were doing a random subsampling and then using low training error samples to pick up the gradient. And there was an issue with non-convexity that was an issue that was critical, and then that was a big innovation in the result from what I could perceive. So the questions I had was the following. So one, this is sort of general questions. So can you think of your sort of systematic error data as, could you even think of analyzing using this method in some sense heteroscedastic data, whereas there are different levels of noise for different samples? They're not corrupted in any way, but just the process by which the samples are generated have different noise. And say that 30% have very high noise and 70% have low noise.
Right. Yeah. Well, okay. So when you say noise, you mean noise in labels? Noise in labels, yeah. Right. So noise.
But I know that the noise levels are different.
Yeah. So
just because of the way the process of, different. Say it's crowdsourced labeling, and then so of course there are different.
Right. Yeah. So if labels are discrete, then I guess noise level. I don't know. The question of noise levels doesn't make sense, right? Because the labels are either in.
This might be for a different setup. In the sense of. I guess I'm talking about maybe some measurements of some sensor measurements, perhaps. It's not in this problem.
Right. Yeah. Yeah. So yeah, they're real valued. Yeah. Then okay, so first of all, the question makes sense even if like the labels are real values, right? And in that case, different noise levels does make sense. So is your question that, as opposed to my setting where like 20% is an error and 80% is great, you have 20% that has some noise and like 50% has some more noise and 30% is great, something like that?
Yeah, something like that. Yeah.
Okay. Yeah, so I guess if you knew those fractions, okay, the naive implementation is just pick only 30% that correspond to what is good, or what is lowest level. But there may be a way to make it a soft version of this thing, right? So this is basically EM, right? So if you think of, like if you think of selection variable Zi for every sample I, right? And then this is exactly EM, right? Or this is hard EM, where in the expectation step, I am making a hard choice on the Z's, but you could make a soft choice on the Z's. And so, if you have noise levels and things like that, it makes sense to have a soft, like a soft version of this algorithm, where you don't, like I am excluding samples and including them, but instead you could just weigh them, and you could weigh it differently.
All right. So the other one was actually related to what Lei was asking. Suppose you didn't know the fraction, and was it possible to even learn it from the data? I mean, there's obviously this trade-off between reducing the samples or increasing the variance of estimates. And
yeah. So we tried a few things. Like for MNIST of. Like if you don't know tau, and then if you have it'll keep working for so the hope was that you start from a very small tau, right? And you run, you run this thing for a few epochs with a small tau. Then you run it for, and that's model one. Then you run it, then you slightly increase tau and you run this for a few epochs, and you slightly increase tau and run it for a few epochs. And the question is that when tau becomes too big, do you see a drop in performance?
yeah.
Yeah, we kind of see it, but it's yeah, I wouldn't say, I mean, I wouldn't say it's an exact science like that.
Yeah, no, it's empirical. It's an empirical and heuristic thing, and some, of course.
Right, yeah.
So the next one was more along the lines of way that people construct adversarial examples or deep learning and other learning schemes. They actually take the data, the strongly adversarial examples actually are the ones that give low training loss. Right? So sometimes what objective is. I mean, I can construct something in a space that is going to give me low loss, but it's going to be a different, I mean, at least for deep learning, I know that some of these methods work that way.
Yeah.
So how would that hurt your scheme in some sense at a high level?
Right. So that is not covered by this, because that is basically errors in features, right? It's like you take an image and then you say, oh, you know what, let me add some like strategically placed speckles.
Yeah.
So that the label is completely changed, but the image looks the same. Right? That's, that is not errors in labels. That's errors in features.
Okay.
Right? So errors in features is a different business. It's a much harder problem.
Okay. And the last one is more, I guess, showing my spots or whatnot. It's when reading through your SGD thing, it was basically had some similarities to the power of D choices, as in you were random sampling and taking the minimum of that and then using that to update the gradients.
Yeah.
And are there ways to use the methods from that literature to analyze this problem? I mean, using the OD analysis or the Stein's method or some mixture of that.
Yeah, so I have thought of, I know exactly what you're referring to, and I have thought about it a lot. It's not clear that it's not clear what the connections are beyond just the fact that you are picking a set and then picking a subset from that.
Yeah, no, I didn't know. That's basically why I was asking. Are there ways to formalize that connection in some sense?
Right. Yeah, I'm not aware.
Okay.
Yeah.
Well, let's thanks, Sujay. Sorry, I took a little longer than
Yeah, no worries.
Thanks for a very entertaining talk. Any other questions from anyone, please? Sorry, I was just giving the formal set of questions that I had thought of. I'll leave it open for others.
Yeah, I'm still curious about loss correction approaches. I know you didn't talk much about label noise, but I see in your paper, I was looking at the ICML paper, it looks like you do talk about label noise. So, and I mean, this is just my intuition. So my intuition is with loss correction, like even if you have a noisy, really noisy example, like instance in your training data, it still can contribute a little bit to the overall objective, to the overall learning goal. Whereas you're kind of throwing those examples away.
Right.
So yeah, I don't know if you compared to loss correction, but I'm just curious how it compares and whether maybe there's a marriage of the two ideas.
So I'll phrase the same point you made in a slightly different way. Suppose my data was not corrupted, right? If I use loss correction and label smoothing kind of ideas, I still get the wrong estimate.
The wrong estimate for?
I mean, it will not be consistent, right? So for example, if I did, like, let's say mixed linear regression, but I change the loss function in the way that they recommend, right? Sorry, suppose I had simple linear regression, right? Like, I think my data is coming from two different linear models mixed together, but actually it's not. It's only coming from one of them, right? But I am going to pretend that it came from two of them, right? And then I'm going to have two different approaches. One is the approach that we talked about today, which is the trim loss minimization. And the other one is loss correction. If I do loss correction, it will not be consistent. It will not find the correct theta star because I'm using the wrong loss, right?
Okay, I was referring to maybe a certain type of loss correction in the multi-class classification setting. So I'm not sure what it would be.
Oh, okay. Which one are you referring to?
So they have names like forward correction, backward correction, loss. There was a paper by some of your colleagues. Naga Natarajan was the lead author, and they had how to modify a loss function if you know the sort of label noise transition probabilities.
Yeah.
But then there was a later work that said, well, that correction isn't really very good for deep learning, but here's a different way to correct a loss. They called that the forward correction. It was a 2017 paper, Petrini et al. So these use the whole data set, but they assume you can or can estimate the label flipping probabilities. And so they use all the data. That's what I was thinking of. Whereas
so they use all the data, but they
it's kind of like a reweighting. Like it's kind of like a way of downweighting the ones that appear to be noisier in a certain sense. But
right, but they didn't have an iterative process, right? Like theirs was a one-shot thing. Like they're what they're doing maybe just one step of our thing. Like it may be the first step. So like, do they reweight samples and learn again?
No, all they do is modify the loss function and then run SGD.
Okay.
So I'm just curious.
Yeah. So I have to go back and see if we compared against them or not. I don't think we did.
You're looking at you looked at like a meta learning setting, which was a little different, where you have an additional clean data set. That's what it looks like. So
We don't have a clean training data set. We only evaluate on a clean data set.
Well, it's like you have a data set, a subset of your training data that's known to have clean examples, I think.
No, we don't need that for this.
I know you don't need it. I know you don't need it. I'm just saying it looks like that's what you were evaluating. How that look. Your competitors are methods that make that assumption.
Okay.
This MentorNet and
Right. Yeah.
learning to reweight.
Right. Yeah. So if you have a small clean set and a big bad set, then you can do many different things. But that's not our setting. And I think, even the original paper you referred to does not have a clean data set.
Right.
Yeah. So no, I don't think we have compared against them empirically. Right. Yeah, I need to follow up on that. I'll take a look.
Okay. Yeah.
Any other questions from
Right. Thank you.
people? Yeah.
Yeah, I have a quick question.
Yeah.
Go ahead. Sorry.
Yeah, go ahead.
You can go ahead.
So one question I had is, how would you propose somebody find this tau? Because it seems like it's sort of like assumed. And then I was also wondering how your method would prevent, or how you would avoid sort of ignoring an underrepresented class that may fall with completely fall within this tau.
Right. So okay. So for the how you find tau, that was what I think Vijay asked in one of his questions as well. And the answer, we don't really have a good answer, right? So if it was linear regression, we can make up an answer, right? But in general, like for neural nets, you need a clean validation set. Right. And so, but then as, Clay pointed out, if you have a clean validation set, you can do other things as well. Right. So in our original setting where all we have is bad training data, there is no real way to figure out tau in a principal way. Right. You can try different values of tau, or you can just be conservative and use a small value of tau to begin with. And that would be better than just ignoring the fact that there is, so any value of tau that you use will be better than just training on the whole data set. Right? But then what's the best value of tau is not clear.
And how would you keep from including or ignoring some underrepresented class by sort of catching it up in this these trimmed samples?
Yeah. So that's a good point. We look at each class and we retain the 75% from that class. Right. So even if everything labeled horse has a high loss, we keep the top, we keep the best 75% of those. Does that make sense? Does that answer your question?
Hi, Sri. I have a question. Is that a conceptual question? So for label noise, can you use some ideas like a robust PCA that because it's an output noise, you can add some sparse, and usually the label noise sparse, you can add some extra term to compensate for the output of the network, and make it a compensation sparse, some regularization on the sparse term. But I guess it might not work because you're using SGD type of algorithm. Yeah,
right. So the thing is that those, robustification of PCA or whatever approaches will work if your learning problem includes PCA as a step, right? But here we don't, right? So I think that's the problem, right? What we want to do is we want to just modify SGD. We don't want to do other tricks.
I see.
Yeah.
Thanks.
Hi, Sujay. For the mixture of linear regression problem, of outputting just a single theta. I was wondering if there is like a minimax lower bound for that, and like what's the best rate we could possibly hope for?
Yeah. So the answer to both things is yes. It's a paper not by me, but by my colleague Konstantin Karmanis. So let me dig it out and send it to you by email. But it's with student Jongyol Kwon, and they have both minimax lower bounds and what is known in so the solution we have is a little bit of a cheating because we need to know the tau, right? But if you don't know the tau, right, then they have an algorithm for that. And so that's a pretty good survey because it's a pretty recent paper. So that would be a good reference point.
Actually, Konstantin spoke about it when he in the series last year. So if you go back to the YouTube video on the channel, you should be able to find it.
Yeah.
Thanks.
So if there aren't any more questions, I want to thank Sujay again for taking
all right, thank
time to
you.
give us seminar. And so I'll talk to you tomorrow then.
Yes, sounds good. All right.